a question which has interested me for a long time, and not only me, is how are linguistic objects, words, sentences, text, their forms and their meaning represented in the brain? And a good starting point, it seems to me, is to try and take seriously linguistics and try to see if the representations that are postulated in linguistics correspond to actual data structure encoded in the brain during real-time language comprehension or production. I should note that some linguists have very early warned against this idea that the objects that they are using are actual objects used by psychological algorithms or not. And they say it's only a descriptive device to put constraints on possible sentences. It has nothing to do with the reality in the brain, but there are crazy people like me or like William, who is going to talk next, who think it's worthy endeavor to try and see if indeed we have these kind of things. I should say that I started my career as a researcher on the problem of speech perception, and I was convinced that linguists were crazy to assume that you compute that speech is associated to this kind of structure, and after 10 years of work, I convince myself from my own data that probably there is something like that around the auditory cortex. And then I moved to syntax, and I'm going to tell you a bit about syntax and semantics, the way we try to ask this question with this representation. So the first thing to say is that the tool I'm using, I'm a cognitive neuroscientist, I'm using a method that allows us brain imaging, that gives you basically time series representing brain activity in different parts of the brain. That's the data we work with. And how do we link cognitive models, psychological models, or linguistic models to brain activity? Basically, we try to correlate the complexity of the processes or the representation with the amplitude of the brain signal. This, in a way, is a very naive approach, but it might be not so crazy. For example, in case of representations, if you assume, say, sparse representation for words, and that the representation of the sentence is kind of superpositions of the activities for words, then the activation is proportional to the number of words, to the complexity, and so on. So you have a very naive model in which it's not that crazy to make this assumption. So I say it's the most common approach, it's not the only one. This is, I think, probably the first paper on syntax and the brain using neuroimaging, a paper from '96 using not fMRI, but the PET scan. This was Karin Stromsworld and David Kaplan. And they put people in the scanner, the PET scan, and they had to read full sentences and judge their goodness, typical task that linguists give to their subjects, although these guys are not linguists. And there were two types of sentences, center-embedded sentences and right-branching sentences. And it was well known at the time already that typically humans have more difficulties processing center-embedded sentences than right-branching ones. And this translates into a pattern of activity in the brain. So the researchers searched for brain areas where the activity was higher for center-embedded sentences than for right-branching sentences, and they actually found a spot here just in the left inferofrontal cortex, also known as the Broca's area. And the interpretation is that some of the computations which are more complex for center-embedded sentences than right-branching sentences occur in this region. Although when you read the article, they are a little bit more subtle than that, and they say, what can it be that creates this increase of activity? It could be the complexity of the syntactic structure, although I don't think they stress that too much, because when you look at it, it's not a priori obvious to say that center-embedded is more complex. Maybe it's not a linguistic fact, it's a psycholinguistic fact that was well known. They say it could be parsing difficulties, the memory load of the parser, or it could be maybe a general verbal working memory limitations. They even say when we ask subjects, they tended to report that they tended to rehearse center-embedded sentences more than the right-branching structure. And actually, this area is also involved in covert articulation, so maybe it's not a crazy idea. What I wanted to show you with that is that it's not obvious to interpret patterns of brain activity and link it to the things. So that's, when I started to become interested in syntax, it was a bit after 96, but not that much after, and I thought we could maybe do better using another approach than manipulating the complexity, which is to use syntactic priming. So the nice thing about syntactic priming is a typical phenomenon that is used in psychology. It's presenting several times stimuli that share some aspects with the idea that the shared aspects makes processing easier the second time. So in the case of syntactic priming, the idea is very naively put is if you repeat sentences with the same syntactic structures and somewhere in the brain you have a representation of this syntactic structure, maybe there will be habituation in this brain area. So the hypothesis is that if I present subjects with repeated syntactic constructions, maybe there will be habituations, and we look where in the brain. The very nice feature of this paradigm is that you always look at the activation, the response of the brain to the same sentence. What you vary is the context, but you measure the activity when the brain reads or hears a car hits the house. And either it's preceded by a stimuli with the same syntactic structures or another one. So you see, it avoids the problem that you had before when you compare different types of sentences. In our experiment, it was performed with Luigi, designed with Luigi, a long time ago. We had 20 participants, and they either read or listened to sentences that were grouped by blocks of 4 sentences, and there were 4 experimental conditions. Either the sentences shared similar syntactic structures. This is the palace that the architect designed. It is a drug, and so on. Or they could share similar lexicosemantic content, but differ in their syntactic structure. Or they could be totally different sentences, and there was a 4th condition, exactly the same sentence was repeated all the time. So searching for repetition priming or repetition suppression in the brains means looking for regions in which you have less activation in condition A than in condition C, right? Different sentences should have more activity than sentences that share the same syntactic structure. The result is on this line. It's a null result. We were not able to detect any effect of repeating the same syntactic structure, while when we repeated the same lexical items and more or less the same sentence meaning, we observed decrease of activity in a good part of the language network in the temporal regions here. So in a way, it was disappointing because we would have liked to find a location of a representation of syntactic trees with a nice paradigm. You could say, okay, maybe your experiment just lacks sensitivity. There is repetition priming, but you didn't find it. Yet I would stress that we were able, under the similar condition, to find very clear effect of repeating the same words. I should also stress that other people have reported syntactic priming effects in brain imaging literature, but they use different paradigms and different tasks, and I think this may be part of the explanation. Another potential explanation is that syntactic trees are actually computed and represented in the brain, but the way they could be represented would not lead to adaptation or habituation. The idea of adaptation or habituation is that you reuse the same neurons, basically. And that's the activation of the same neurons is lower the second time. But imagine that the way you implement syntactic trees is not done by precise neurons, but rather by, say, synchrony between lexical neurons. Then maybe this would not yield syntactic priming. Another possibility, and I could list actually many potential postdoc explanations for this null result, but the last one is that syntactic parsing might be optional. especially when the task, I didn't tell you, but the subjects in my scanner, they were doing nothing, just reading the sentences and from time to time press a button just to make sure that they were not sleeping. But I do that because I don't like people to perform syntactic goodness judgments in the scanner, because then the brain activity is very different from normal brain activity. So I tend to put people in the scanner and tell them, read what you see. But at the same time, it doesn't really force them to do much with the sentences. And it had been reported, for example, by Peter in the Fray, using fMRI, that he didn't also see syntactic complexity effects in this situation in comprehension while he saw them in production. So that's a possibility. And we investigated it with Shotiga Patamadilok a while ago. We asked the questions, are complete syntactic trees computed automatically? And we used a design quite similar to the one of Karin Stromsworld and David Kaplan before. So we had two types of sentences, center-embedded sentences, like the kids who exhausted their parents slept, versus adjunct construction. Even if the kids spoke loudly, their parents slept. So people were in the scanner reading these sentences, well, one sentence, and just a bit after the sentence, there was a probe flashed on the screen, and the probe could be the kid slept, or the parent slept, or the dog barks, and they had to judge whether the probe was entailed by the preceding sentence. So basically a yes or no, or unrelated response. Unrelated was like no. We can measure reaction time, and you have reaction time in dark gray to center-embedded sentences, and in light gray to adjunct constructions, and you clearly see that people are faster when you have adjunct rather than center-embedded, and the classic interpretation in psycholinguistics would be center-embedded sentences are more complex, more difficult to process than non-center-embedded ones. But one nice thing you can do with brain imaging, although fMRI is not the best tool for that, you can disentangle the response of the brain to the sentence and to the probe. You do that by modeling separately the sentence and the probe. And in this experiment, in the end, we can measure four things. We can measure the response to a center-embedded sentence here, or to a sequential adjunct sentence, or to a probe following a center-embedded sentences, or to a probe following a sequential sentence. And when we run a contrast comparing center-embedded versus sequential, we can do it on the sentence or on the probe. And the finding here is, I could have put an empty brain, I didn't even put anything. We didn't detect any difference on the sentences, but we detected very clear difference on the probes when people had to perform the decision task and kind of analyze the sentence in detail to check it. Moreover, remember there was a case of unrelated probes, and in the case of unrelated probes, there was no difference neither on the sentence nor on the probe. So that means that we didn't detect any complexity effects that are usually reported when you use reaction times, or remember in the case of Stromsworld and Kaplan, they used grammaticality judgments, goodness judgments. So there could be two potential conclusions. The first one is, again, maybe we are using a tool, fMRI, which is not sensitive enough to detect a complexity effect. So maybe center-embedded sentences are more difficult to parse, but the parsing cost is tiny and we don't detect it with fMRI. Or maybe people don't perform the full syntactic parse unless they need it to answer a question. You should realize that I've been able to tell you things only with no results until now. And now I'm going to try to show things with positive results. So for about 20 years, people doing neuroimaging and language have done, myself and other people, this type of task. But over the last 5-6 years, more and more, we have moved to a more ecological situations of understanding full text. With the interest that that's the natural task. I mean, you try to understand the text and that's it. And you don't present sentences in isolations, or in my case, very often, list of words, things which people could do crazy things. That more and more, there are teams in the world who are putting people in the scanner, make them listen to an audiobook or make them read text, although reading is more complicated, and measure brain activity and try to relate brain activity to cognitive variables of interest computed on the text. So in my case, with colleagues in the US, John Hale and Jonathan Brennan, we used an audiobook of The Little Prince lasting about 90 minutes. We mark the word onsets and offsets, and we have cognitive models where you compute variable of interest. It could be, say, for example, just the lexical frequency of words. You can put this in the model, and you can search for brain regions where the activity co-varies with the frequency of items, and you say, oh, that's probably lexical recognition region. One of the very pioneers of this approach is Jonathan Brennan, who published this paper in 2012, where he had the subjects listen to a 30-minute portion of Alice's Adventure in Wonderland, 9 subjects, and he computed, he had from the past trees of the sentences, the number of syntactic nodes above each word and how many nodes you close, and he correlated brain activity with the number of syntactic nodes you close word by word, and found a little spot here in the anterior temporal cortex. So this was one of the earliest attempts to use this approach, and it was new and interesting, although I think most people, including Jonathan, would probably not believe that this is the locus of parsing this little spot. One of the reasons is that, first, it's not necessarily where you expect it, plus it's a little bit small, and actually, when you look at more recent data, that's data that I obtained with John Hale and Jonathan Brennan, where here we have 50, so 5 times more participants, a longer piece, and we correlate the number of actions of a bottom-up parser, so more or less the same idea. We find activations a little bit everywhere in the language network, both on the right, both on the left. So on the one hand, previously you had a suspiciously tiny spot. Here you have a suspiciously large network of areas. One of the reasons is the difficulty with naturalistic stimuli is that you put some variables in your model, some predictive variables, but there are tons of variables that co-vary with that. Even the acoustic energy of the signal could co-vary. Well, we put it in the model. I didn't tell you all the confound variables we put, but there could, for example, in this map here, there was no semantic predictors. So if there are any semantic features that correlate with the number of reduced actions, this would have been picked up by your model. So I don't want you to live with the idea that this network is doing parsing and only parsing. Now, if you turn to semantics, you can, we started to do something that was with Valentina Gliosi here. We uncrafted some semantic categories. So it's the Little Prince text, 1 hour and a half. And she tagged all the words mentioning locations, all the words mentioning numbers, all the words mentioning animals in the text. And there were about 300 such words in the text, which has a total of 15,000 words. And to my amazement, most of the time, the brain areas where activation correlated with the occurrence of this type of words were exactly what you would expect from neuropsychology or classical neuroscience. If you take locations, you had activation in the para-hippocampal place area. If you take numbers, you had activation in the intraparietal cortex. We also had colors with just a spot like where you expect it. So I was myself, I had difficulty believing it was working that well. At the same time, you can only uncraft a few categories, and there are many semantic features for which you don't have enough words in the text. So you cannot go very far with this approach. At least to me, it shows that we are not only capturing noise, we are capturing things that are interesting. So one way to go beyond this uncrafted feature is to use models such as the one we have seen previously, especially Word2Vec by Mikolov yesterday, and other models. And I'm going to show you a few results we obtained in the lab, not yet published with that. So using NLP tools such as latent semantic analysis, Word2Vec, or GLOVE, you can associate words to numeric vectors, and I think Benjamin said they are this is kind of encoding the context of occurrence. This is distributional semantics, although I hesitate to use this term because I think it probably also captures some aspects of syntax, given the context. So I don't think it's pure semantics. I will not claim that. But that captures the context of occurrence of the words, and it encodes them into numeric vectors. And you can use these numeric vectors to correlate them with brain activity. So in particular, we use GLOVE, which is one class of search vectors, 300 dimensions. So we have our brain signals, a few thousand data points per voxels in the brain, and we try to predict them from the 300 vectors from GLOVE. And I will not enter into the details, but in the end, we obtain cross-validated correlation scores between the model and the data. And the first finding is that you find that most of the brain can be partly explained by your features. And this is not only us. This has already been shown by Huth and Gallant, for example, and other people. And for me, it was a bit surprising. Actually, when I saw it for the first time in someone else's publication, I thought, oh, this seems to be too much. But we find exactly like them in our lab. And a very quick interpretation would be to say semantic information is distributed everywhere in the brain. This proves embodiment. That is, when you process language, you activate all sensory areas and so on that are used in action and so on. Okay, maybe. I will come back to these R values. But before showing more, I wanted to tell you that so GLOVE, Word2Vec, they are kind of dictionaries. So there is a static representation associated to each word. But our subjects, when they were listening to the reference, they were hearing words in context, right? For example, if there was an ambiguous word, they could disambiguate it from the context. So we we introduced in our analysis models that take into account the context. So incremental models in which you give as input to the model the preceding text. Or even sometimes when you use BERT, is a kind of transformer model which is bidirectional. You can even give it the future that helps the system perform better. Clearly, the humans don't do that, but these are the transformers, these crazy things. Coming back to the GLOVE and actually the other model, the first thing you can do is look at the distribution of R values across the whole brain. So in our images, we have information in relatively small pixels, a few millimeter cubes. And here are the distributions of R scores for GLOVE in green, for a LSTM model in blue, for GPT-2 and for BERT in green, in red and black. And here you have a random model where we put random values to the thing. So all these R values, which are quite small, actually, if you go 0.05, it's a very weak correlation. Still, they are highly significant. So when I showed you the brain saying it's all activated, yes, it's very tiny R, but highly significant. I think it's useful also to, so these are tiny R's, but they are not so tiny when you compare them to a model, to an estimation of the maximum correlation that you can get from the data without any model. So model 3, imagine we have 50 people, we can compute all the correlations between pairs of people, and this gives us an estimate of the best correlation you can get. Actually, that's not the algorithm we are using a more clever one. But we have a measure, totally model-free, just from the data of the subject. They all listen to the same text, remember? So we can correlate their maps, and we have in each voxels of the brain the maximum signal we can explain. When we normalize these R values by these model-free R values, we reach 50% for a GPT-2 and BERT. So we explain about 50, well, our R is more exact to say our R values are half of what they can be at the maximum. So there's still a lot we don't know, but there is still some we know a fair share. Now, you can use these models to try and understand. We were interested in the sensitivity to context. So the first thing, so how important is the context, and especially what brain regions are using the context to compute a representation. And the first way we approached the problem was by comparing an incremental model, for example here GPT-2, versus a static lexical model, GLOVE. And here you have a map showing the regions which are predicted significantly better by GPT-2 than by GLOVE. And you see especially the angular gyrus, the precuneus here, DMPFC, and so on. But I actually think that because we played with many models, this kind of picture is actually misleading, because when you compare GPT-2 versus GLOVE, for example, you have to know that they are just not trained on the same data set, and it's nearly impossible to train them on the same data set because they require data sets of different order of magnitude. So this type of comparison, I think, doesn't help us very much. And even comparing any network that differ in their structure, because for the moment their structures are so different from the brain, it's not so useful. What is more interesting is to use a single model, and for example, what we did here, vary the size of input we give to the model. So we gave either the full little prints to the model, or we gave it for each word a certain number of words of context, okay? So the models are trained on the same data set, but they are run on the little prints, but masking words out of a context window. And we increase the context window size. And here you have a plot of a region giving you an idea of the window of integration of information. In yellow, this is where we detect differences between 40 versus 15 sentences. So it's quite long away context. Actually, it's something that surprised me in all this analysis. You could go quite far and still add to the fit. I hesitated to include this picture because it's actually not that stable. When you change model, it varies a bit. So this is unpublished data, and more to give you the idea of what we are trying to do than as a definitive result. Now, this is not us, this is Charlotte here, and I think with Jeremy King, they recently published a paper with a beautiful idea, which is to try and disentangle syntax and semantics by starting from a text. So they didn't use the little prints, but let's pretend they used the little prints. So using the text, the little prints, and the brain activation associated to them, and then you create new text that only share the syntax. So you create colorless green ideas, type of stimuli based on the little prints. It's very hard and it's not perfect, but still. And you compute predicted brain activations from your model, and you do this many times with many texts. And you can then apply this, look for correlation with the actual brain activation elicited by the little prints. And before looking at the results, you might have found, if I do that, I will see the syntax network. Well, maybe this is the syntax network, but this is again a huge network. We see huge activations everywhere. And I'm not totally able to interpret this. This is a fact that I'm giving it to you. I think this type of approach has only started strongly like 1 or 2 years ago, and we are still trying to understand what it should. Oh, I think I went faster. Another thing you can do a priori is, and this has especially been done in the field of visual processing, on the field of vision. This deep network, the name deeps, comes from the fact that they have several layers. In our case, we used models that had about 12 layers, state-of-the-art models that you find on the market. And you can ask whether different layers predict the signal in different parts of the brain. That would be very cool to try and claim, look, this layer is computing different type of information and this overall. This is not what we find. And I think Charlotte is here. Maybe she could confirm in her data too. I don't know. But we find that in all the regions of the brain, we have about the same curves of increase in fit when we give the activation of a given layer. So it's as if a new layer adds information on top of the previous one, but it's not deleting so much. My graphics are not very clear here, but here we tried our best to show a dissociation, an interaction between depth and the depth and the air value that you get. And we could sort of identify it on the raw graphs, but to show it more clearly, here we split the graph in first and second component, and there are just these two regions here that don't behave exactly the same, so they reach their plateau in the middle layer, and these are the auditory regions. So it looks like for the prediction of auditory regions, it's enough to go in the middle of the network. Now, maybe some of you should have had an N400 reaction to what I just said, because, or maybe I didn't stress this enough, but all these models, BER, GPT, they are trained on text corpora. And we get to make the prediction, we make the prediction from the little print's text, written text, while the subjects were listening to the print. So in a way, it could seem a little bit bizarre that you can predict activation in the auditory cortex from this model. But so we have only post-hoc explanations. You can predict things like pauses, for example, or end of sentences or stuff like that. So maybe that's the explanation. I don't know. I'm not sure. But again, these models, they don't predict at the phoneme level or whatever. 2 minutes, perfect. This is my last slide. What have we learned in this presentation, at least? I told you that maybe we do not systematically compute the full syntactic structure of sentences. This is not to say that there is some automatic syntactic processes that I'm sure, and you can see them with EEG, if you have gross syntactic violations between successive words. So it's not that we are doing syntax totally optionally, but whether you compute the full tree, I don't know. Now, turning to studies with naturalistic stimuli, they suggest that they give a pictures of the brain which are quite different from the one we used to see in our classical subtractions. Maybe before we only saw the tip of the iceberg in a way, or the things that was common to all the sentences, and that with naturalistic text we are pick up much more signal even from a few words in the text. That's fairly possible. At any rate, it looks like most of the brain is engaged during language processing. But I want to stress one thing, and this has been stressed a long time ago already by Cathy Price, who is both a pioneer of neuroimaging of language and a neuropsychologist. And she remarked that in fMRI, we see lots of activation, but maybe not all of them are necessary for language processing. So we are not sure whether they are causally involved in language comprehension. The only way to know would be to poke holes in the brain or use other techniques. So I warn you against the idea of that this picture shows that you need the whole brain to understand sentences. I mean, this is a much more complex question. We do not see, for the moment, or maybe never, clear dissociation between syntactic and semantic computations, or sensitivity to syntax and semantic, but there is so much that remains to be done that I prefer to just be descriptive, saying I don't see much dissociations. Maybe they will come out, maybe they won't. And clearly there is a topic that came back several times in these 2 days. It's very clear that we need to better understand information encoded in deep nets. And I'm talking about information encoded and not the structure, because I think a bit like Roger Levy yesterday, I don't believe that the structure of this network maps on the structure of the brain, but I think they extract information for the task. The information is there in this network. Then we know they manage quite impressive tasks. So I'm using them more interested in the type of information they extract that in their structure. But we need to understand how this information is encoded as much as we can, and that's work that a guy in my office, Yair Lacretz, has started to do with Marco Baroni and Stan Dehaene. And for example, because they managed to isolate some subpart of the network that encode more syntactic features, we can separately correlate activation of this subpart of the network with brain activity. So it's just the beginning. I don't think I gave you any firm conclusion. I just gave you a picture of what we and other people are doing nowadays.